Okay, so this conversation we start now talking about chemical reactions. And an important aspect of chemical reactions is describing them, and we're going to describe them with something we're going to call chemical equations. Between you and me, I don't like the term chemical equations because there's no equal sign. Now, having got that out of my system, let's talk about balancing chemical equations. We're going to use symbolism, right? We talked about the symbolic domain, and we're going to use symbolism that gives both identities and relative quantities. And we're also going to talk about physical changes, chemical or physical changes. All right, so an example would be this. Suppose we took methane, which is the primary component of natural gas, right? We took methane. Here's a picture of what methane might look like, a space filling model. Carbon is the black ball in the middle, and then 4 white spheres on the outside will be the hydrogen atoms. If we took methane and we burned it in air, it importantly has oxygen in it, then we could get carbon dioxide and water, all right? So can you see that you've got 4 spheres here, right? 4 hydrogens, right? There's the 4 right there. Get those 4 little white spheres. And you've got 4 over here too, right? So you've got 4 hydrogens on the left side, 4 hydrogens on the right side, which is exactly what you would expect if you were hoping to, quote unquote, balance a reaction. All right. So this example illustrates the salient aspects of chemical equations. Importantly, we've got reactants on the left side, products on the right side, and we have plus signs, which means that we have that's things that are being added together, and the arrow means that we're separating that from the reactants from the products. So the arrow means it produces, right? That's how we read the arrow. A plus B produces C plus D. The relative number of reactant and product species are represented by coefficients, right? And the coefficient could be moles, it could be atoms, or not atoms, it could be moles, it could be particles, it could be molecules, it could be dozens, right? It could be pairs, things like that. All right, but they're essentially coefficients give the ratios. All right. Now, it's common practice to use the smallest whole number coefficients in a chemical equation. So oftentimes when people say something is balanced, what they mean is it's the smallest whole number coefficients. These coefficients represent the relative number of reactants and products, and so therefore they can be considered to be ratios. All right, and that's exactly what they are. So in the previous example, methane and oxygen react to yield carbon dioxide into 1 to 2, 1 methane to 2 oxygens to 1 carbon dioxide to 2 waters in a 1 to 2 to 1 to 2 ratio, right? And that's a completely legitimate way to write that. So let's look at this as a picture, and then we'll be done with this part of our conversation. So if we're thinking about methane and carbon dioxide, we said 1 to 2 to 1 to 2 ratio, right? But here I've got, look at that, looks like I've got a 3. There's 3 methanes, right? To 1, 2, 3, 4, 5, 6 oxygens. You see the 6 oxygens here? And then I'm making 3 carbon dioxides. There you go, 3. And then it looks like there's 1, 2, 3, 4, 6 waters, right? So you can see that this is the same reaction. And you know what? This ratio is the same. You see 3 maps to 1 as 6 maps to 2, as 3 maps to 1 as 6 maps to 2, right? So it doesn't matter the absolute number of molecules involved. The ratios stay the same. All right, so that's an introduction to balancing chemical reactions. Obviously, we're going to be doing more about that in the upcoming conversations. We're going to give great more detail. But for now, balancing chemical reactions introduces us to the idea of reactants, arrows, which mean produces, right, and products. And it also represents us to the coefficients, which tell us how much, the relative amounts of each of the reactants and products.